I'm just get you to have a look up here. I'll do a quick recap of what we learned about yesterday, because this was pretty important, and we're really going to affirm what we've done here, because that's going to help us in our assignments. It's even going to help us today. So what we did yesterday is we just started with some definitions of angles. Okay, remember I said they're arbitrary. It could be anything, but what we use conventionally is 360 degrees for a whole revolution, which means half a revolution is 180 degrees, and a quarter of a revolution is 90 degrees. Okay, and then from that, we were able to prove that vertically opposite angles are equal. Okay, so we've already got one property of the line, and we're also able to prove that the angles on the line add up to 180. That's by definition. So we've got those two properties. And then we have these parallel lines, and we're able to make this axiom, make this claim, boys. All right, that these two angles, they look equal. Okay, they look like they're equal, and we can measure them with our protractor, and we can see that is the case. And we could do this 10, 15, a million times. And it's going to affirm, Ruben, it's going to affirm what we've proposed, but it's not going to prove it. Okay, it doesn't prove it in every case. It only proves it in the million cases that we've performed it. All right, so there's always, maybe there's an exception out there. Okay, but from that axiom, we were then able to prove all the other rules in terms of parallel lines. Okay, so what have we done? We started with, this is important because it's going to build up to your assignment. We started with some definitions, and we derived these rules. Okay, we use these rules, and then we witness here, we've got this sort of, this axiom. Okay, what's an axiom? It's something that we can see to be true, but we can't prove it. It's something that we have to assume. And from that axiom then, we're able to derive all the other rules of parallel lines, like alternate angles are equal, and co-interior angles add up to 180 degrees. And so then from this one axiom, we've built up a whole mathematical system. Okay, from one thing we can't prove, we've built up this whole system. And we're going to take it even further today with triangles. Okay, so we're going to transition from parallel lines into triangles. So the concepts that we're revising, we've done in Year 8 Maths. Okay, so the concepts are easy, but what we're looking at is, how do we know that this is the case? Noah said, this is important, guys, listen. Okay, how do we know that this is the case? So we're going to prove both of these rules today. All right? So we obviously know that angles in a triangle add up to 180 degrees. That's something we've been taught, maybe even since primary school. But why is that the case? Well, that's what we're going to prove today. And then this is the other one here, that the exterior angle of a triangle is the sum of these two interior angles. A plus B is equal to A plus B over here. We're going to prove that rule as well. This one's a little bit more complex in its proof. So I'm going to go through this one first. And then I might try and provide a little bit of instruction and get you guys to have a go at proving this one. Okay, so this is what we're trying to prove. So we're not going to start with it. So we're going to follow along here. This is in the proof properties of triangles. That's what we're going to start with. We're going to fill in that box there. We're going to fill in that proof. We are going to start with parallel lines because that's what we've been talking about. Okay, we're going to draw two parallel lines. All right, they're going in the same direction, they have the same slope, they're the same distance apart at every point. Parallel lines. And within those parallel lines, we're going to draw a triangle. So I might just draw a line through here, and then a line going through here. Okay? All right. And then let's put some letters in. Okay, so this point can be A, B, C, D, E, F, G. And maybe try to put the letters in the same position that I have, just so that when we're performing the proof, we can make sure we've got the same notation. Okay, then we're just going to define a few angles to begin with. Let's begin by letting angle CAB equal alpha. Okay, so CAB, that's going to be this angle here. This is alpha. All right, now these are parallel lines, aren't they? All right, and we know from our rules in parallel lines that corresponding angles are equal. So what does this angle correspond with? This angle here, angle ECD. So we know, therefore, angle ECD is also alpha. This angle is equal to this angle here. All right, because they're corresponding. So we need to, we've stated a relationship. We need to provide a justification, and that is corresponding angles in parallel lines. Excellent. And then we're just going to do the same. Let's let angle ABC equal, let's say, beta. All right, so this angle here, angle ABC, that's going to be beta. And we'll make the same assertion. What corresponds with beta? This angle here. These are our parallel lines. And so the same relative position is going to be this one here, angle FCG. Okay, we can start to see where we're going with this. And then let's define this last angle here, angle ACB, this one in here. Let's let angle ACB, let's let it equal phi. Okay, planet. Let's let it equal planet. So this is phi, and therefore angle FCE is also going to equal phi, because they are vertically opposite angles of intersecting lines. So that's angle FCE. Vertically opposite angles. And I need to provide a justification here as well. And we can see now, right, GD is a straight line, okay? So let's make this statement. GD is a line, and so therefore angle alpha plus beta plus phi is equal to 180 degrees. And alpha and beta and phi are all of the angles inside the triangle. And so all of the angles inside the triangle are going to add up to 180 degrees. Therefore, angles in the triangle add to 180. Okay, so isn't that just absolutely amazing? Right? We've started with one single axiom, and we've built up this whole mathematical system. Here we've proved that angles in a triangle add to 180 degrees. Okay? So it doesn't matter what the triangle looks like. It could be any triangle. We haven't dictated the size of any of these angles. They could be any number, and the relationship holds. So let me give you some instructions for this proof. Okay, let's give you some instructions for this proof and see if you can do it. We'll start with just a triangle that looks like that, with this line. That's a straight line going out like that. And we'll just label them A, B, C, and D. Okay, so now what we're going to do, I'm going to issue some vocal instructions. I'm not going to write anything up here, so just listen very carefully and see if you can carry it out. All right, does everyone look up yet? So we're going to let this angle equal alpha. Not yet, just watch. Let this angle equal alpha. This angle can be beta. And then I want you to go, well, what's this angle going to be if we know that all angles in a triangle add up to 180 degrees? It's going to be 180, take away that angle, take away that angle. And then this is a straight line. So that means this angle here is going to be 180, take away this angle here. Go ahead and perform that, see what your results show. anyone still on this first whiteboard? Or need anything? Just draw your attention up here, we'll just have a quick chat about it. So this is what we've said. We've said let angle BAC equal alpha, okay? Let angle ABC equal beta. And that means that this angle here, okay, therefore angle ACB, this angle in here is going to be 180, take away alpha, take away beta. And then I've said, but this is a straight line. So that means that this angle here is going to be, so that's BCD, is going to be 180, take away this angle here, which we saw was that. So we've got 180, take 180, take alpha, take beta. So 180, take 180, that cancels, and we've got negative alpha is positive alpha, and negative beta is positive beta. So look at what we've done, right? We started with, these are our definitions, okay? Vertically opposite angles are equal, and angles on a line add up to 180 degrees. We assumed that corresponding angles are equal. We've got good inductive evidence to assert this. And then from there, we've derived this whole system. Look at that, co-interior angles are equal, alternate angles are equal. The angle sum of a triangle adds up to 180. And then if this is true, then we're even able to derive this rule even further. So you can see how this whole geometric system is built up on these definitions and this one axiom. Excellent. So let's do the example. Let's turn the page. I'll just point out right at the bottom there, I've got some definitions about isosceles triangles. So that's important. So isosceles triangle is a special case of triangle where we have two sides are equal. Okay? If the two sides are equal, that means these two angles are also going to be equal. And if the two angles are equal, it means the two sides are equal. And the line coming straight down the middle, we say bisects this line. If it bisects it, it means this side and this side are equal to one another. And because it bisects it, this meets at 90 degrees. So there's a lot going on in an isosceles triangle. If it satisfies any of those, all right, two sides are equal, two angles are equal, bisection line or 90 degrees, then it's by definition isosceles triangle. Okay, so we're going to use these a little bit. Let's move over to our example. And we'll fill in our notation here as well. So let's do our notation first, and then we'll talk about our example. So the first piece of notation in your notation box there is just angle, sum, triangle. All right, that's the quick hand way of writing it, and you would have seen me write that up here as my piece of evidence for why we can make that assertion. Okay, our second one is going to be exterior angle of triangle. And our last one is just going to be isos triangle. Alright, so we've got three pieces of notation there that we're going to use. Now, let's have a look at our example. I will write this out so we can draw a picture. So we have, this is 38. We're told these two sides are equal. This is x, and this is y. Alright. So what we're going to know, and I'm going to put some letters in here just so that we can prove it properly, so that we're making the statements properly. Angle ACB is equal to x. How do we know that? These two sides are equal, which means it's an isosceles triangle, which means the angles, look, the angles dictate how long the side is. That if this angle's bigger, then that side's going to be longer. If it's smaller, then that side's going to be shorter. So because the sides are the same length, that means the angles have to be as well. So here we have angle x. All right? And then we can do, well, x plus 38 is equal to 180 degrees. And provide a justification, angle sum triangle. And so we've got 2x is equal to 180, take 38, 142. So x is 71. Okay, and then we've got two ways now we can make the claim about what's the size of angle y. Okay, we know that x plus 38 equals y because it's the exterior angle of a triangle. Or we know this is a straight line, and so y is going to be 180, take away x. Either's fine. All right, let's do the exterior angle of a triangle because we've done lots of straight lines already. So we're going to say, therefore y equals x plus 38. And let's provide a justification. Our justification is the exterior angle of a triangle. Okay, that the two interior angles add up to the exterior angle, provided this is a straight line. It can't just be an extra line going off in any direction. This continuum, AD, must be a straight line. Okay, let's solve this now. We know x is 71 plus 38. We've got 109. Excellent. So that'll be enough to get straight into our work booklet. We're just working through today. What's it say on the front there? Question 5 and 6.